165 years. That's how long the Riemann hypothesis has sat at the top of mathematics, completely unsolved, with a $1 million prize attached to it, and the collective brainpower of every great mathematician since 1859 failing to crack it. Today, we're diving into a paper published in the Journal of Mathematics Research in June 2026 that builds what its author calls a kernel lattice criterion, a framework that is claimed to be mathematically equivalent to proving the Riemann hypothesis. By the end of this episode, you'll understand what the hypothesis actually says, how this new symmetry normalization framework approaches it, and why the irrational frequency argument at its core is so striking. I've got someone here who has gone deep into this paper, so let's get into it. Walk me through what we're actually dealing with.
So the Riemann hypothesis, at its core, is a statement about a specific mathematical object called the Riemann Zeta function. And the claim is that all of its so-called non-trivial zeros, the input values where the function equals 0, lie on a single vertical line in the complex plane, the line where the real part of the input equals 1/2. That line is called the critical line.
Okay, so what does 0 of the zeta function actually mean, like in plain language?
Right, so the zeta function takes a complex number as input and spits out another complex number. A 0 is just an input where the output is exactly 0. The trivial zeros are well understood. They sit at the negative even integers. The non-trivial zeros are the mysterious ones, and they all seem to have real part exactly 1/2, but nobody has been able to prove that's always the case.
And why does it matter? Like, why does the math world care so much about where these zeros sit?
Because the zeros of the zeta function encode information about the distribution of prime numbers. The explicit formula, which goes back to Riemann himself, connects the zeros directly to how primes are spaced along the number line. If all the zeros are on the critical line, the primes are distributed as regularly as possible. If any zero wanders off that line, it would introduce irregularities in the prime distribution that we've never observed, but also never ruled out.
So it's like the zeros are the heartbeat of the primes.
That's actually a really good way to put it. And what this paper does is build a new analytic framework, the kernel lattice method, that translates the question of where the zeros sit into a question about the symmetry of a certain function on a discrete grid. And the claim is that the symmetry holds if and only if all the zeros are on the critical line.
Okay, so before we get into the machinery, the paper introduces this idea of even-odd decomposition. Can you break that down?
Yeah, so any function at all can be split into two pieces. An even part, which is symmetric around 0, and an odd part, which is antisymmetric. The paper calls functions that have both pieces mixed class functions. And the key insight is that a non-trivial 0 of the zeta function is precisely a point where the even energy and the odd energy cancel each other out perfectly. The paper calls this a pure non-trivial 0, a state of perfect equilibrium.
So the 0 isn't just a place where the function happens to be 0, it's a structural balance point.
Exactly. And that framing is important because it tells you why the critical line at 1/2 is special. The paper argues that 1/2 is the unique point in the normalized interval from 0 to 1 where the even decay rate and the odd rotational rate enter perfect resonance. Move above 1/2 and the even part dominates and suppresses the odd part too fast. Move below and the odd part overwhelms the even part. Only at 1/2 do they balance.
That's actually kind of elegant. It's not arbitrary. It's the midpoint of the normalization window.
Right, and the paper formalizes this through what it calls the normalization completeness theorem. Every admissible cancellation event, every place where a 0 can structurally exist, is representable within the normalized height window from 0 to 1. Nothing outside that window introduces new independent zeros. The window is complete.
Okay, so now let's get into the actual kernel construction, because this is where the paper gets really specific. What is this cotangent kernel?
So the kernel is the function k of x, which equals cot of x times cot of a times 1 minus x, multiplied by a normalization function na of x. The cotangent factors supply what the paper calls intrinsic oscillation. They encode the symmetric halves of the unit interval. And the normalization function na corrects the parity and phase so that the whole product is even under the reflection x maps to 1 minus x.
And why cotangent specifically? Why not some other function?
Because the paper shows that this cotangent structure is not arbitrary. It's the continuum analog of the normalization gear inside the functional equation of the completed zeta function. The functional equation says xi of s equals xi of 1 minus s. And when you unpack that symmetry, the cotangent product is exactly what falls out. So the kernel is engineered to mirror the zeta function's own internal symmetry.
So the kernel is basically a reflection of the zeta function's DNA.
That's a great way to say it. And actually, the kernel is constructed completely independently of the zeros. It doesn't know where the zeros are. It's calibrated purely from the analytic structure of the functional equation. That independence is what makes the framework non-circular.
Wait, that's actually a big deal, right? Because a lot of attempts at the Riemann hypothesis have been criticized for assuming what they're trying to prove.
Exactly, and the paper is very explicit about this. Lemma 12 in the paper formally proves that the construction of the explicit formula and the analysis of its symmetry properties do not presuppose any information about the location of the non-trivial zeros. The kernel is a probe of the spectrum, not a mapping that moves zeros around.
Okay, so now we have this kernel. What does it actually do?
It gets inserted into the explicit formula for the logarithmic derivative of the completed zeta function. The result is a function a of x, which the paper calls the kernel lattice transform. This function decomposes into a zero sum, contributions from the non-trivial zeros, plus a remainder term na of x. And the key structural fact is that the remainder is an even function. It has no odd component.
So the remainder is purely even, and the kernel is purely even, which means if anything odd shows up in the full transform, it has to come from the zeros.
Precisely. That's the setup for the contradiction argument. The paper defines the odd companion, the odd projection of the remainder, and shows that it must vanish identically on the sampling lattice. If it doesn't vanish, the functional symmetry of the zeta function is broken. So the question becomes, when does the odd companion vanish?
And the answer is only when all the zeros are on the critical line.
Right. Here's the mechanism.